In this lecture, we will look at the relationship between Gibbs free energy and reaction equilibria. Living systems are always away from equilibrium, and therefore we need to understand reactions both at equilibrium and away from equilibrium. If you look at the PowerPoint, then the reaction we are looking at is right here, where A moles of compound A react with B moles of compound B to form the products C and D. By definition, the Gibbs free energy of the reaction can be defined in two ways. The first definition is up here. So, the reaction Gibbs free energy is equal to the Gibbs energy, the derivative of the Gibbs energy with respect to the number of moles. A more intuitive definition perhaps is the second one, where the reaction Gibbs energy is simply the number of moles of the products multiplied by their chemical potentials, because the chemical potentials are nothing but the molar Gibbs energies. So, it is the products minus the reactants. If you look at the graph on the right, it shows you how the Gibbs energy varies with the composition of the reaction mixture. On the left hand side, you only have reactants, and on the right hand side, you only have products. At this point, the slope of this line is negative, which means the reaction Gibbs free energy is negative, and because it is negative, the reaction will go towards the products. At this point, the slope is positive, and again the reaction will now go towards the reactants. At this point, the slope is 0, and the total reaction Gibbs free energy is 0, and this is the definition of chemical equilibrium, chemical reaction equilibrium. So, the definition is that the total reaction Gibbs free energy is equal to 0 at equilibrium. So, let us see how this Gibbs free energy changes, the reaction Gibbs free energy changes with respect to composition. So, the reaction Gibbs free energy for the reaction that we just wrote, where A moles of A react with B moles of B to produce C moles of C and D moles of D, can simply be written as the Gibbs free energy of C plus the Gibbs free energy of D minus the Gibbs free energy of A minus the Gibbs free energy of B. And these can be written in terms of the number of moles and the chemical potential. So, the first term is the number of moles of C multiplied by the chemical potential of C, and so on for the products and for the reactants. Now, each of the chemical potentials, now remember this is not under standard conditions. So, this can be broken down a little bit more, remembering that the chemical potential is given as the standard chemical potential plus RT log of the activity for any component I. Yes. So, if we substitute this equation into this, we get C times the standard chemical potential of C plus RT times the activity of C plus D, the number of moles of compound D, multiplied by the standard chemical potential of D plus RT log of the activity of D, and then you have similar terms for each of the two reactants. Okay. And now we can isolate each term. So, let us isolate each term with standard chemical potentials. So, what we get is C mu C, this is number of moles of C multiplied by the standard chemical potential of C, and then we can make similar terms for both the reactants. So, this is one term. And then I can write all the other terms in this way. I can take out RT, so I can say minus RT, plus RT, the number of moles of C multiplied by the activity of C, the number of moles of D multiplied by the activity of D, and so on. And for the reactants, there is a negative sign. Good. Now, let's remember some simple math. X times log of y is simply equal to log of y to the power of x. Yes. And when we substitute this here in the second term, let's do the second term first. We get RT multiplied by the logarithm of the activity of C multiple to the power of the number of moles of C, activity of D to the power of number of moles of D, divided by the same terms for the reactants. So this should be small a and this should be capital A. You also have to remember that log of x plus log of y is equal to log of xy. So I have used both these relationships to come up to condense this second term. The first term is nothing but the standard reaction Gibbs free energy. So I can write that as reaction Gibbs free energy and use this symbol to denote standard. Yes. So let's try to summarize this again up here. The reaction Gibbs free energy for this reaction is equal to the standard reaction Gibbs free energy for that reaction plus the universal gas constant multiplied by the temperature multiplied by log of the activities to the power of the individual number of moles. Now the activity can be a concentration or a partial pressure depending on which phase we are in. Now this product on the right is often called the reaction coefficient. And we are going to denote with Q. So what we get is that the reaction Gibbs free energy is equal to the standard reaction Gibbs free energy plus the gas constant temperature times the logarithm of the reaction coefficient. This is true for any reaction that is occurring at constant temperature and pressure, whether it is at equilibrium or not. What happens at equilibrium? At equilibrium, the reaction Gibbs free energy is 0. So at equilibrium, 0 equals the standard reaction Gibbs free energy plus RT, and then at equilibrium, the reaction coefficient becomes the equilibrium constant. And this gives us finally the relationship between the standard reaction Gibbs free energy and the equilibrium constant for any given reaction. And this is a very important equation, of course. Yes. So the reaction Gibbs free energy for any reaction occurring at constant temperature and pressure is equal to the gas constant, temperature multiplied by the logarithm of the equilibrium constant. And the equilibrium constant here has been defined in terms of activities and not in terms of concentrations. The activities can be a concentration, they can be a partial pressure, depending on which system you are looking at.